Google's Willow chip has learned to detect and correct its own errors, while computations run continuously, without shutting down the entire system. Unlike your laptop that rounds away electrical noise instantly, quantum computers operate as analog machines where every control signal must be precisely calibrated. Quantum processors are controlled by microwave signals with exact frequency, amplitude, and phase values that must stay stable throughout computation. The fundamental problem is hardware drift. Temperature shifts, material defects, and qubit behavior changes cause control parameters to become incorrect over time. When control settings become stale, every quantum gate operation injects fresh errors into the computation, compounding the damage. Until now, the only solution was to stop the entire computation, recalibrate everything, and restart. Impossible for algorithms requiring days or months of continuous runtime. Algorithms that quantum computers need to solve, like simulating chemical reactions or breaking encryption, require continuous operations spanning days to months without interruption. Quantum error correction uses redundancy to protect information by weaving many physical qubits together into one robust logical qubit. Specialized parity checks provide binary error or no-error signals without measuring the actual quantum information, since measurement would destroy the superposition. The decoder receives detection events and must infer which errors occurred and where, converting analog noise into actionable digital corrections. Google's neural network decoder Alpha Qubit and algorithmic decoder Tesseract process detection events to identify the most likely error patterns and generate corrections. Detection data reveals symptoms of calibration problems, but traditional systems never analyzed this data to understand why errors occurred in the first place. Decoherence is unavoidable fundamental physics, but a huge portion of remaining errors come from drift in control parameters that engineers can fix. Traditional quantum control used physics-based modeling to build accurate system descriptions and designed dedicated experiments to calibrate parameters one by one. Hand-built models hit performance ceilings as chips improved, and exotic error sources appeared that the models never anticipated. Computer vision, robotics, and protein folding all broke through similar ceilings when machine learning replaced rigid theoretical models with data-driven approaches. Google repurposed error detection data that was already flowing continuously, giving it a second job alongside traditional error correction. A reinforcement learning agent applies tiny perturbations to all control parameters simultaneously and learns which nudges correlate with improved performance. The agent cannot directly optimize the logical error rate, which is exponentially suppressed and requires enormous sample sizes to measure accurately. Instead, the agent optimizes average detection event rates across all detectors, a cheap proxy that correlates strongly with the logical error rate. Each detector only affects nearby control parameters, creating thousands of small independent optimization problems instead of one impossible thousand-dimensional problem. This sparse structure is why the approach scales. Adding more qubits adds more sub-problems, but does not make any individual one harder. The agent uses a policy gradient algorithm that samples candidate control policies, ranks them by detection rates, and nudges the distribution toward better performers. Google tested the agent on Willow by unleashing it on already heavily calibrated hardware, with decades of human expertise and physical intuition baked in. The agent achieved an additional 20% suppression of logical error rate on top of existing optimization, a significant improvement that human experts had missed. Willow's distance 7 surface code achieved a logical error rate of 7, 72 times 10 to the minus 4 per cycle, meaning 1 error per 1,000 correction cycles. The distance 5 color code achieved 8, 19 times 10 to the minus 3, roughly 1 error per 100 cycles, the best performance on any qubit platform demonstrated. In the second experiment, Google deliberately injected artificial drift into control parameters using step changes, sine waves, and stroboscopic pulses across the entire qubit grid. A fixed control policy degraded predictably as parameters drifted stale, but the agent continuously tracked the drift and maintained performance. When a step change was applied to pulse amplitude, the agent recovered in approximately 130 learning epochs, demonstrating concrete reaction speed. The agent achieved a 24% reduction in error rate and a 2.4-fold improvement in stability against injected drift. When the agent was given control of decoder parameters as well, improvements jumped to 31% error reduction and 3.5-fold stability improvement. Fourier analysis revealed the agent acts like a low-pass filter, removing approximately 4 decibels of amplitude from low-frequency hardware fluctuations. A stress test deliberately scrambled control parameters into complete chaos, destroying logical information, and the agent recovered to high performance from scratch. This recovery from scratch suggests reinforcement learning could eventually replace significant portions of the entire calibration stack, not just polish existing methods. The same reinforcement learning technique improved magic state cultivation by an order of magnitude in error rates and post-selection rates. Simulations tested scalability by modeling a distance 15 surface code with roughly 40,000 control parameters to be optimized. The critical finding is that training epochs required scales independently with system size, not gently or logarithmically, but completely independent. Detection events are local, so adding more qubits adds more independent subproblems without making any individual problem harder. Convergence follows a clean exponential law dependent on parameters per gate, not on total machine size or qubit count. One genuine limitation exists. Learning requires exploration, meaning running control policies worse than the current best, which causes real errors during long algorithms. Simulations found a critical drift frequency around 1 per 150 epochs, below which real-time steering beats a fixed policy. Above that critical frequency, the agent cannot keep up with drift, and cosmic ray strikes fall into this problematic regime requiring hardware solutions. Currently, the agent uses a simple Gaussian policy, because data bandwidth between the quantum processor and classical controller is too slow for complex neural networks. Increasing bandwidth would allow training deep neural networks conditioned on real detector outputs, enabling the system to discover hidden correlations automatically. The endgame vision is a processor calibrated entirely from scratch by a machine learning agent with no physics models or human experts needed. This approach does not depend on superconducting circuits and applies equally to trapped ions, neutral atoms, or whatever quantum hardware platforms emerge next. The path to quantum fault tolerance has always been framed as a hardware story, requiring better fabrication and cleaner materials. This work reveals that control is equally crucial to fault tolerance, and machine learning is exactly what engineers need for solving control problems at scale. The full research is published open access in Nature, providing detailed mathematical formulations and complete experimental protocols for implementing this approach. Don't forget to subscribe and turn on notifications to stay informed of the latest videos.